In this video, you're going to learn about CPU shares, which is a way that control groups can limit the CPU of your application. CPU inside containers is definitely one of the more complicated topics, and it's the one which is likely to cause you problems in production. So it might be worth coming back to this video and the next one on CPU quotas. You might think, isn't it simple? Surely I just set what percentage of a CPU that a container can use. But unfortunately not. First off, even if we only had a couple of containers on a machine, if a CPU becomes underutilized, so let's say that your processor in production stays at 10%, what ends up happening is that the CPU itself, to save the environment, will start powering itself down. And that's not what we want. We want high utilization. So instead, control groups give us three different mechanisms for limiting the amount of CPU that have various trade-offs. These are CPU shares, which is what we're going to cover in this video, and they're a relative share of the CPU divided between containers. Then we've got CPU quota. So we'll be looking at that in detail in the next video, and that is about saying this container can use this amount of CPU time. So 100 milliseconds every second, for instance. And then finally, there are CPU sets. I mention these because for completeness, but they're not typically used in production environments for inside environments like Kubernetes. And what they do is they pin particular containers to certain CPUs. So now let's have a look at CPU shares. CPU shares are probably the most common mechanism used for Java applications in production. It is the default in Kubernetes, but you can also use quotas, which we'll discuss later. So they are a relative value. What does that mean? Well, it means that we're going to give a number to each container, and that number in isolation means nothing. What it is it's relative to another container. So if one container has one CPU share and another container has two, then the second one will get double the amount of CPU. But it'd be the same as setting the first container to 100 and the second container to 200. So it's important to understand that when you describe a container in production that you're trying to understand perhaps why it's not performing, you can't just look at its CPU shares. You have to look at what other containers are running on the same machine. So let's look at an example. So imagine that you have a 2-core machine and we have 3 different containers. We've got an orange one, a blue one, and a green one. If we were to set the orange one to 1024 and then the 2 other ones to 512, then it's kind of like giving the first container a whole core and then splitting the other core between the other 2 containers. Just like knowing the value of one container is not useful, the CPU share of one container, it's also not useful knowing the value unless you know how much CPU the box has. So if we were to move these 3 containers with the same CPU share values onto a different machine with just one core, then suddenly the orange container is only going to get 1020, only going to get about half a core, and the other 2 are only going to get about a quarter of a core. This can be quite puzzling when your application suddenly degrades in performance. It could be just that your container orchestrator has moved it to a different host with a different configuration of CPUs, or alongside different containers with different CPU share values. The next important thing to understand about CPU shares is that they are only enforced when the CPU cycles on the machine are constrained. So if we have 3 containers on the same machine, with their CPU shares set to the same, say they're all set to 1024, if 2 of them don't want to do anything, they're idle, so they're not receiving any user requests, then the first container can go wild. It can use all of the CPU, which is a really good feature of CPU shares to keep utilization high. Because CPU shares are only enforced when there's contention on the machine, they are fantastic for resource usage. If your goal is to move to containers to save money by utilizing your underlying hardware, or say your cloud virtual machines better, then CPU shares are the way to go. And we'll compare them to CPU quota in the next video. So CPU shares are a feature of control groups. So how does Docker use them? Well, you can explicitly set CPU shares when you start your container. And by default, they all get 1024. So if you want to increase the relative value for your Docker container, then you should increase it above 1024. So if you've started a bunch of containers with no value for this, and you want to start a new one which has higher priority on the CPU, you need to set it to above 1024. So if now that we understand CPU shares, how does this affect Java? We learned in the JVM ergonomics that a lot of things in Java are configured based on the number of cores. But we've learned about CPU shares is that we can't equate them to a number of cores because it's dependent on how many cores are on the machine that we're running on and what other containers are running on that machine. So Java has decided to treat 1024, which is Docker's default value, and it's also used in Kubernetes as a special value that we'll see later, as one core. So if you give a container 1024, then Java will treat that as one core. But if you give it, say, double that, so 2048, it will treat it as two cores. So all of my thread pools would be sized based on two CPUs. This is an interesting decision because if nothing else is running on the machine and we have 128 cores, our Java applications will size its CPU and its threading based on the CPU share value with this formula. The fact that 1024 is treated as a core. So our container might be running on this big beefy machine, and unfortunately it wouldn't be able to utilize it because it wouldn't have enough threads. So this is something to watch out for. A conclusion for running Java inside Docker using CPU shares is that we should also use a scheduler or a container orchestrator that follows the same rules as Java. So Java basically treats 1024 CPU shares as a core. And if our scheduler does the same, for instance, we want a scheduler that if a machine has 12 cores, it puts 12 times 1024 worth of CPU share on that box. Then suddenly Java's treating 1024 as one CPU will work well. Otherwise, the JVM will pick an incorrect number of cores, which in turn will misconfigure garbage collection, the just-in-time compiler, and all libraries which set their thread pools based off the number of cores. Now let's demo CPU shares in Java with various versions of Java. At some point in Java 8, it started following the formula that we've just described. However, before that, in Java 8 update 131, then CPU shares were completely ignored. So rather than artificially constrain our thread pools by treating 1024 as one CPU, we had the opposite effect. Even if we had a container with a small share of the CPU, it would end up with thread pools and garbage collection configured as if it was running on a big beefy machine. So, now that we understand a bit about how Java behaves with CPU shares, let's do some demonstrations. So we're going to use the CPU shares submodule in the samples project. The main difference is that this is going to be targeting Java 8. And we're going to do that because we want to test various versions of Java. We'll end up using 11, but I want to see older versions of Java 8 against the current version of Java 8 and see the behavior differences when it comes to running inside a container. We'll use a very simple class to test this. It does two things. It prints out the number of cores, which is the thing which many different libraries and frameworks use to size their thread pools. And then finally, we'll print out the fork join pool parallelism. And that's the thread pool which is used to execute things like your parallel streams. We'll start with an oldish version of Java 8. So Java update 102, and we'll use a JRE. We're inside the samples project here. We need to build the Docker image. So that's just our normal Gradle W CPU shares Docker. This will take a moment or two, as I think this might be the first time we've used this base image, so it'll take a while just to download the base image. and then we can try run it. So the image has been built. We can verify that with Docker images and search for CPU shares. It's quite large, 309 megabytes. Now let's just try and run it without any CPU share settings. So it's come up with 8 cores. And where's it got that number from? Well, I'm running on a Mac at the moment, and that Mac has a Docker Desktop. Docker Desktop has a certain number of resources, and it's 8 cores. So there's a mini virtualization layer for Docker to run on when running inside a Mac. And it's actually that virtualized system's number of CPUs that's been based on. If you were to run this same demo on Linux, then it would be your actual server or laptop's number of CPUs that would be based on. But we haven't actually provided any configuration for CPU shares yet, so maybe that's a good default. But how about if we add 1024, which is kind of like 1 core, but we still get the 8 cores? Okay, that's odd. How about if we tie a bigger number like 2048 and it's still 8 cores? And the reason for this is because we're using an old version of Java. There is no container support in the earlier versions of Java 8. And that's why it's just so important that you're using the latest version of Java, even if you're still stuck on Java 8. So let's change this to 8JRE Slim. That will pick up the latest version of Java. That tag just points to the latest version of Java for Java 8, and it will be a JRE, and the Slim version, so the slightly smaller one. So if we need to rebuild the Docker image now, so we'll do that with our normal Gradle W Docker command. That will take a little while because we've got a new base image to download. And now that that's done, let's try and rerun it. So let's make sure it's built. Yep, we've used Slim, so this image is a little bit smaller. And now let's do a Docker run, and we're going to run CPU shares. Now, without any configuration, nothing has changed, but let's add in some CPU shares configuration. So let's start off with 1024. So nothing's changed. That's a bit surprising. We'd have expected that with the latest version of Java 8 to pick up the number of cores based on CPU shares. But if I switch it to 1025, it suddenly flipped to 2 cores. That's a bit weird. What about 2048, so 2 times 1024? Yep, that's 2 cores as expected. Let's try some slightly bigger values. And this is 3 cores because it's just over 2 times 1024. And then finally, let's try 3 cores. So it's 3 times 1024, and that works. What we've just noticed, or what we've just seen, is that Java has this formula of shares divided by 1024 to work out the number of CPUs, but it does not adhere to that formula for one CPU. That means that if you pass in 1024, it doesn't treat it as one CPU. Instead, it treats it as the number of CPUs on the box. This can have devastating consequences for your applications in production. You might give your application half a core, and that would actually, if we did a number below 1024, it would round up to 1. And then suddenly, if you changed it, you thought you were increasing the CPU a tiny bit to 1024, it could suddenly take over the entire box because it will suddenly size all of its thread pools based off the number of the cores on machine. This is very weird behavior, but it's something that you have to be aware of when running Java inside a container. So finally, let's just validate the behavior of Java 11. So we'll switch our image to 11JRE Slim, rebuild the Docker image with the normal Gradle command, and then run through some of these same scenarios. So let's wait for the Docker image to build. And now that's done, let's just run some of the experiments again. So 3072, we get 3 cores as expected. Let's try some different values. So with nothing at all, we get the same behavior. It uses every single core on the machine. And then let's try the funny one again. So let's try 1024, not 34, sorry, 1024. And again, so Java 11 still has this same behavior as Java 8 when you give your container just 1024. So that's it for the demo for CPU shares. In the next video, we'll go through CPU quotas, which is an alternative way of limiting CPU of your containers.